Okay, this is the quick video to guide you through the notes on hyperbolas for Chapter 11, specifically Section 11-2, but hyperbolas. Hyperbola has a series of important concepts in them. First of all, these purple lines are called the asymptotes, and you'll notice that the hyperbola gets closer and closer and closer to these asymptotes without ever actually touching them, which is, of course, what an asymptote does. It also has two focus points, or foci, that happen to be, again, inside the conic section. Okay, so they're in here, and excuse me, they're a certain distance from this vertex here. You may also be able to see that right here there's this kind of a rectangle, a bounding box rectangle that, here I'm going to scroll this up a little bit. You'll notice that dotted line rectangle. The asymptotes go from corner to corner on that rectangle, and the hyperbola is contained within that. So I'm going to move this up here for now. Let's see, we'll snap that to, we'll snap it to right there. I'm going to move this vertex up here. And yes, it is actually possible to have a rotated hyperbola or any conic section, but we're going to stay away from those for right now. Now, within that exact same rectangle and the conic section that's formed by it, this is the horizontal variant. Okay, so the distance from the center to the direction the hyperbola is going, that's called A. And we'll come back to the notes on this in just a second. But the direction the other way that this thing is going vertically is the B value. And then, of course, the distance from the center out to the focus point is letter C. Now, if I switch this, I'm going to shut off the horizontal version and turn on the vertical version. You'll notice that the asymptotes haven't changed. V1, V2, center, none of those things have changed. These golden lines, none of that's changed. The rectangle's identical. Everything is the same. But look where the focus points are now, and the hyperbola is going up and down instead. So with the exact same rectangle, the exact same set of asymptotes, we can get two different hyperbolas just depending on how the equation is built. Okay, so both of these are possible. All right, let's switch back to these notes here, and we'll start filling in a few things. You'll notice that everything is more or less, already kind of filled in. I've got the vertical. You can see I've got this kind of homemade rectangle drawn in here for both of these. The main feature for both of these hyperbolas is what letter comes first. Over here I've got the y first, so that means this thing is going up and down. And over on the other side, I've got the x coming first, which means that this thing is going left and right. Okay, so we can tell some information about it by looking at the equation itself, which one comes first. And you'll notice that the a is underneath whatever came first, because on a hyperbola, the subtraction sign kind of forces one thing to come first instead of the other. Okay, we'll come back to this concept right here, the length of the LR, which we haven't talked about yet. And also, I already mentioned this in the sketch or the dynamic geometry sketch, but the foci are outside the rectangle, but they're inside the conic section itself. Okay, so we're going to work on this particular conic section right here, the one highlighted in green, which I can tell is a hyperbola because it's got the subtraction sign there. And I can tell because the x comes first right here that this must be a horizontal hyperbola. Here are some facts. They're printed already in your notes there. They're already written out. The direction that the thing opens is called the transverse axis. Okay, the transverse axis. Now, we can't really call it a major and a minor axis because that changes. The major axis we kind of think of as being the big one, but it doesn't have to be. If I wanted a vertical hyperbola, the direction, this transverse action, is smaller than the conjugate axis. So you got to always pay attention to which way it's going, and that's why we can't use a handy-dandy notation like major and minor. All right, so let's start filling this stuff in. Since our example has x minus 2 coming first, this thing opens horizontally. And the center is at the coordinate 2, comma, negative 4. And I'm hoping you all recall that, and that is where that came from. The transverse axis, remember the transverse axis is the direction that it opens up. So since this thing is opening up horizontally, and A happens to be 4 because A squared is 16, then that means the whole transverse axis is 8 units long. And the conjugate axis, which is the one going in this case vertically, that would be the value of B, which, because B squared was 9, B is equal to 3, this thing must be 6 units long. Okay, so we're going to have to start by drawing a rectangle centered at the center. Duh. All right, I got to pause for a second. Okay, so I'm going to move over here and sketch out a rectangle that's centered at 2, -4. And magically, I've got that starting there. So let's see. So 2, -4 would be right about here. Okay, so that's my center point. And let's see, I want to draw my rectangle because A is 4 and it's going horizontally. I'm going to go 4 units to the right. So that would put it right here, and 4 units to the left. And then I needed to go 3 up and down in each direction. Remember, I'm counting by 2's on this particular graph, and I'm going to create this, my blue rectangle right here. And unfortunately, I don't have fantastic purple ink on this particular program, so I'm just going to draw the asymptotes in, going from corner to corner through the center and through here. Okay, so those are my bounding asymptotes. Now I'm going to jump back here and take a look about this. All right, plot the vertices. Think about the edges of the rectangles. I just did that. Draw the asymptotes, corner to corner through the center. I just did that. What I'm going to need to do here is identify what these coordinates are, because those are always, always, always important. Let's see, I'm going to draw an arrow to here. So that coordinate would be at 6, -4. This coordinate would be at -2, -4. Not the vertex, but the bounding box of the rectangle up on top here would be to -1, and this guy here would be at 2. Let's see, I was down at -4, and then I went down 3, so -7. All right, so I got those identified. The next thing I want to do is come back here and consider the Pythagorean theorem. Now, let's answer these questions. Which is always bigger in this case, A, B, or C? Well, because the C, this distance out to the focus, is clearly outside the rectangle, then C has to be the biggest. So it's going to have to fit this kind of description, C squared equals A squared plus B squared, and it doesn't actually matter which one's A or B in terms of this problem. So when I come back here, I'm going to do my little work down here. C squared equals A squared plus B squared, so C squared, A squared was, I believe, 16, B squared was 9, and naturally I've picked convenient numbers for me. So C is equal to 5. So that means the distance from the center to the focus is 5 units. All right, so I'm going to go back up here, and I'm going to count out, because I remember this thing is traveling horizontally. I'm going to make sure that I go out 5 units this way, which is, it's really only one further than where I'm currently at. So that focus point will be at, let's see, 7, -4. And this focus point will be at -3, -4. Okay, so that makes this 5 units here and 5 units here. Okay, so I'll call that F1 and F2. I do sometimes take the lazy way and do something like this. Since I know my focus point is at -2, and then I'm supposed to, in this case, subtract 5. I'm sorry, my center, I lied. My center was at +2, and I'm supposed to subtract 5, -4. And then over here, I could have also done my center plus 5, -4. I occasionally do that when I get yucky square root numbers for my C value, but in this case, it was a nice, easy number. So I would probably just use the exact focus points. Now I actually have everything I really need right this moment to sketch in my entire conic section. It starts at these vertices and it approaches the asymptotes in both directions. Make sure that it doesn't go through the focus point. Now remember, this is just a rough sketch of the conic section, so I don't really care if it's perfect, but what I would look for is that it starts at these vertex points and it approaches the asymptotes, doesn't touch them. Alright, so let's move back over here to the notes. Let's see, so I've got find the asymptotes. Now I like to use the point slope form right here. Okay, so that's my favorite. And I don't really, there are formulas in the book that you can look at and everything, but I don't like to do that. The thing that I know for sure is that the asymptotes go through the center and the corners of the rectangle. Okay, so it's pretty straightforward to figure out the slopes of these things. So I'm going to come right back up here and I'm going to figure out, let's see, I'm going to use green for this dot here and of course the center. So as I count out the slope, I can see that this thing is going up. Let's see, it was down here at -4, so it's going up 3 and to the right 4. So the slope is up 3 and to the right 4. And I also know that it goes through the center point. Down here on the other asymptote, the slope is going down 3 and to the right 4. So the only real difference is that one of the numbers is positive, one of them is negative. Okay, so as I consider this this equation right here, I'll do the top one first. I know that I'm going through the center point, which is at -4, and my slope was 3/4, and I'm going through the center point x minus 2. So I'm actually okay with just leaving it like that, but of course you could simplify it into y plus 4 equals, you could distribute that if you wanted to, and then subtract 4. I don't know, I don't see any reason to do all that work, so I'm going to leave it like that. And then here on the bottom side, I'm going to have almost identical stuff, except my slope is opposite sign. So I actually kind of started getting in the habit of, when I consider my two equations, that I use this. I go y minus the -4 equals plus or minus, because I know the slope is going to be one of those two, and then x minus 2. And I just leave it like that for the equations of those asymptotes, but you do have to find them. Okay? All right. Okay, so now we're going to introduce a new term, which is right here. Yes, it's the latus rectum. He said rectum. Yeah, I don't know. It's Latin for something, okay? But the important part is that it is a segment that goes through the focus point and is perpendicular to the, I'm going to actually put two things in here. It's either perpendicular to the major or it's perpendicular to transverse axis. Transverse, nice spelling, okay? So let's go back here and take a quick look at our pictures. Okay, so on, let's see, going all the way back to the beginning for all of my things. All right, you'll notice here I've got this green line sketched in. That is the latus rectum, the LR. Over here, the latus rectum would be right here. Oops, let me use it in green. Right here. That would be the latus rectum. There's two of them. They're going to be the exact same length. So since this particular conic section that we've been working on is a horizontal one, that means the LR is this segment right here and right here. Now, I don't normally draw them in, but that's where they are. They end on the hyperbola, so they've got points that are on the hyperbola, and it goes right through the focus point. But the important part here, and this is true for all conic sections, that the length of the latus rectum is this formula, 2b² over a. Okay, so we're going to use that formula. That's the length. And I'm going to do that back up here for a quick second. Let's see. So the LR would be 2 times b squared. In this problem, b was 3, so b squared is 9, and a was 4. So 18 over 4, or what is that, around 4.5? So that tells me this segment here should be about 4.5, which seems pretty close. You know, I've got 2 this direction. Right here is 2, and right here is 2. And this must just be a quarter and a quarter. So I could actually find that point if I really wanted to, but I don't really want to. Okay, so for right now, okay, wait, formula is 2b squared over a, and the answer was 2 times, whatever it was, 4.5. You saw that already. Okay, now what I want you to do is on the back, try this. And the next video is going to give you the answer to that, where you can check all your solutions. Make sure you find everything: the asymptotes, the equations of the asymptotes, the length of the lattice rectum, the focus points, everything.